Hi, I'm Dave Mueller, retired hydrologist from the U.S. Geological Survey and founder of Genesis Hydrotech. In this session, I'm going to discuss the ADCPs and the different modes they use to accurately measure the water velocity depending on conditions, how the ADCP profiles the water column, how it bottom tracks, and how it determines depth. Let's discuss some of the commonly used ADCPs. This is not a comprehensive discussion, and the absence of an instrument from this discussion should not reflect negatively on the instrument, only that I don't have sufficient experience with the instrument to discuss it. If you watched my video discussing how ADCPs measure the Doppler shift, you should know that optimizing the lag is one of the keys in obtaining the best possible measurement of velocity. I'm going to discuss the Rio Grand and StreamPro because understanding the modes available on these instruments will help understand what the smart ADCPs are doing automatically. For the Rio Grand, the lag, or ambiguity velocity, must be set manually. That is the main purpose of the configuration wizard. The StreamPro has a fixed ambiguity velocity of 3.4 meters per second, except at shallow, low flow, where a pulse coherent mode may be used. Smart ADCPs, such as the River Ray, River Pro, Rio Pro, and River Surveyor M9, S5, and RS5 automatically adjust lag, ping type, cell size, and processing based on the prior samples and characteristics within the current signal. The Rio Grand was one of the first ADCPs designed specifically for measuring inland waterways. The Rio Grand was released by Teledyne Ardrey Instruments in the late 1990s. These instruments usually have a frequency of 600 or 1200 kilohertz, though some units may have a frequency of 300 kilohertz. The Rio Grand typically utilizes 4 operational modes: water modes 1, 5, 11, and 12. These modes and their depth cell sizes must be selected prior to data collection. The Rio Grand data is collected and processed in Wind River 2. Direct connection to the unit is possible with the provided cable, but the user may supply wireless communications. Mode 1 is the basic mode. The WV command is used to set the radial ambiguity velocity. The ambiguity velocity must account for both the water and boat speed. Modes 5 and 11 are the slow velocity modes. The lag is equal to the depth, so only one of the pulse pairs is active in the water column at a time. The result is the ambiguity velocity would be so low that these modes would be impractical. One of the techniques used in water modes 5 and 11 is to get a rough estimate of velocity in a portion of each profile called the ambiguity resolving bin, or ARB. This estimate is used to limit the expected range of velocities for the measured depth cells in the profile. The primary difference between water mode 5 and water mode 11 is where the ambiguity resolving bin is located. For water mode 5, the ambiguity resolving bin is located near the water surface, and for water mode 11, it is located near the center of the water column. The goal is to locate the ambiguity resolving bin where there is low shear and high backscatter, so that the estimated velocity is close to the true depth cell velocities. The water surface and the stream bed are the more likely sources of shear, so water mode 11 is the default choice in these conditions because it locates the ambiguity resolving bin near the center of the water column. Occasionally, locating the ambiguity resolving bin near the surface, as done by water mode 5, may work better. Water modes 5 and 11 utilize a technique called bin-to-bin tracking to dynamically set the expected velocity for each depth cell. The use of this technique is what allows these water modes to measure very precise velocities. The estimated velocity from the ambiguity resolving bin sets the expected velocity range for the depth cell nearest the center of the ambiguity resolving bin. As the velocity is calculated for the depth cell, the measured velocity, along with the estimated velocity, is used to estimate the velocity for the neighboring depth cell. This process is repeated until it has tracked through all of the depth cells in a profile. If a true velocity for a depth cell is outside of the expected range, it can cause an ambiguity error in that depth cell. Note that ambiguity errors in water mode 5 or 11 are generally caused by an incorrect ambiguity resolving bin estimated velocity and result in a velocity error for all of the depth cells in an entire profile. Water mode 12 can be thought of as an optimized mode 1 averaging multiple pings. Mode 12 reads the sensor once, then does multiple mode 1 type pings. Mode 1 requires the sensors be read with each ping and thus ping slower. Mode 12 also averages in the complex phase plane before transforming the data to velocities. Mode 1 transforms the data to velocity and then averages the velocities. The advantage of averaging in the complex or phase plane can be understood in this example. The ADCP measures 4 pings. In mode 1, those pings are transformed into velocities, and then the velocities are averaged. So a 40-degree phase change is transformed to a 38 centimeter per second velocity. A 110-degree phase change is transformed to 107 centimeters per second velocity. 140 degrees phase change is transferred into 136 centimeters per second velocity. And 210 degrees results in an ambiguity error and is transformed into a negative 146 centimeters per second. Mode 1 then averages each of these transformed velocities and reaches a mean velocity of 34. Mode 12 averages in the phase plane, so it would average 40 degrees, 110 degrees, 140 degrees, and 210 degrees, reaching an average of 125 degrees, which is then transformed into actual velocity of 121 centimeters per second, a significant difference between 34 and 121, and shows the effect that an ambiguity error can be minimized using the average in the phase plane. Now that we have introduced the Rio Grand water modes, let's talk about the order of preferred use. Generally, we try to use the low noise modes first. That would be modes 5 or 11. However, these can only be used with small bends in shallow water. They have a limited application with a max velocity of about 1 meter per second and a max depth of about 4 meters for a 1200 kilohertz and 8 meters for a 600 kilohertz. If the water is too fast, too deep, or too turbulent, mode 12 is the next choice. It has a high ping rate. It does allow for small bends with a minimum depth of about 1 meter. However, it has potential errors in dynamic conditions because, as you recall, it only measures the sensors once at the beginning of each ping. If the conditions are very dynamic, mode 1 is probably the safest choice. It's a robust mode. It can collect data in more conditions if deep enough. However, it has high instrument noise, more variability in velocity and discharge, and has limited bend sizes. The required minimum depth to use mode 1 is deeper than modes 5, 11, or 12. The measurements you see here were all made on the Ohio River. At the top, the color contour plot is data collected with water modes 5 or 11, and we can clearly see the distribution of velocity is displayed. However, we do notice that there are a lot of white striping indicating that this is right on the edge of the viability of modes 5 or 11, and it is struggling to collect data with every ensemble. The middle color contour plot was collected with water mode 12. Again, we can clearly see the velocity distribution within the cross-section. We notice that the cell sizes are bigger, that the ensembles are wider due to the longer time it takes to measure a mode 12 ping, but it still provides a very clear representation of the velocity in the cross-section. The bottom plot was collected in the same cross-section with water mode 1. We'll first note that 2 spots here indicate that communications were lost momentarily in water mode 1 and resulted in these rather large width depth cells. However, the thing that we want to observe is the fact that the data look very random, and identifying the distribution of the velocity within the cross-section would be very difficult. The important thing between these three measurement modes at the same cross-section is that the discharges were nearly identical, because there is enough data collected that the random noise was averaged out, and all of these modes resulted in nearly the same discharge. So now let's look at the StreamPro. The StreamPro is a 2 MHz ADCP designed for shallow water discharge measurements. The minimum depth is about 15 centimeters for 2 good depth cells. The maximum profiling depth is about 2 meters for the standard version and approximately 6 meters with the extended range optional purchase. It has a maximum of 30 depth cells. A small float is included, although an optional larger boat is available and is recommended for higher velocities. Optional midsection measurement software is also available, as is an optional compass. The StreamPro only communicates through Bluetooth. The default mode for StreamPro is mode 12. It's a modified multi-ping mode 1 or modified mode 12 type ping. It includes 8 full pings that are averaged together to obtain 1 ping. This is not user configurable. The number of water pings is set to 6 by default. Therefore, each water mode 12 ping actually provides 48 averaged pings per ensemble. The ambiguity velocity is fixed at 3.4 meters per second. The long-range mode reduces the number of pings in each average ping. The WP, or the water ping, stays at 6. And the idea is to maintain an ensemble data rate of once per second. StreamPro Water Mode 13 is a long lag pulse coherent mode. It transmits 2 pulse pairs, 4 pulses. The first pair lags slightly longer than a range to the stream bed. The second pair has a lag of 1.5 times the lag of the first pair. It averages 30 pings in phase space and resolves ambiguity using a proprietary scheme. However, Mode 13 is very limited and typically only works in less than a meter of water and very low velocities. The RiverRay, RiverPro, and Rio Pro are TRDI's auto-adaptive or smart ADCPs. The RiverRay is a flat-faced, phased array 600 kHz ADCP. The 4 beams are generated from the single phased array transducer and emit from the ADCP at a 30-degree beam angle. This results in a larger unmeasured area, particularly near the bottom. The newer units also contain a 600 kHz vertical beam. The RiverRay comes with an integrated float. It has built-in Bluetooth communications. You can add additional data radios to the RiverRay as well as GPS. The data are collected and processed in Wind River 2 software. The RiverRay has no manual configuration, but is always dynamically configured as the measurement is made. The profiling range is approximately 0.5 meter to 40 meters. The RiverPro is a 1200 kHz ADCP that is similar to a Rio Grand in that it utilizes a 4-beam Janus configuration at a 20-degree beam angle, but has an additional 600 kHz vertical beam used to measure vertical velocities and depth. The profiling range for the RiverPro is roughly 30 centimeters to 24 meters, which fits into a range between the StreamPro and RiverRay. Like the RiverPro uses auto-adaptive sampling, meaning it will configure itself as it moves across the river. Unlike the RiverPro has the ability for the user to manually override the configuration, fixing it for an entire measurement, much like a Rio Grand. The RiverPro has built-in Bluetooth, but can also be used with a direct connect cable or radio modems. The Rio Pro is essentially a Rio Grand that maintains the housing of the Rio Grand, but has its electronics replaced with the RiverPro electronics. The River Ray, RiverPro, and Rio Pro have two types of bends. First are the surface bends or depth cells. They're small, they're always pulse coherent, they always require ambiguity resolution. For the River Ray, those bends are always 10 centimeters in size. For the RiverPro or Rio Pro, they may be 6 centimeters or 12 centimeters in size. The use of the surface cells allow for depth cells measured closer to the water surface. Below the surface bends are the regular bends similar to those of a Rio Grande, but are automatically adapted to the velocity and depth of the flow. This table shows the regular and surface cells for the River Ray and RiverPro Rio Pro for various depth conditions. The River Ray for a depth greater than 10 meters will have a regular cell size of 80 centimeters and 5 surface cells of 10 centimeters. For a depth range between 10 and 15 meters, the regular depth cell size will be reduced to 40 centimeters, but there will still be 5 10-centimeter surface cells. Between 5 and 2 meters of depth, the regular cell size will be reduced to 20 centimeters, and there will be 3 10-centimeter depth cells. For the RiverPro and Rio Pro, between 40 and 15 meters, the regular cell size is 96 centimeters, and there are 5 12-centimeter surface cells. Between 15 and 6 meters, the regular cell sizes are reduced to 48 centimeters, and there are 5 12-centimeter surface cells. Between 6 and 3 meters, the regular cells are reduced to 24 centimeters, and there are 3 12-centimeter surface cells. Between 3 and 1.5 meters, the regular cells are reduced to 12 centimeters, and there are 2 12-centimeter surface cells. Between 1.5 and 0.5 meters, the regular depth cell size will be 6 centimeters, and there will still be 2 6-centimeter surface cells. Below a half a meter depth, the depth cell size will be 2 centimeters. This figure from the Wind River 2 user guide provides an example of a change from 3 surface cells on the left to 5 surface cells on the right for a river ray. It is important to note that even when the number of surface cells or the size of the regular bends change, the cell boundaries continue to line up. When there are 3 surface cells and 20-centimeter regular cells, the bottom of the first regular cell lines up with the bottom of the last of the 5 10-centimeter surface cells. Next, let's look at the SonTek River Surveyor M9, S5, and RS5. The M9 is a 9-beam, 3-frequency profiler. It has 4 beams at 1 MHz, 4 beams at 3 MHz, and 1 beam at 500 kHz, which is a vertical beam measuring only depth. The velocity profiling range is between 0.3 and 40 meters when using bottom track. The S5 is a 5-beam, 2-frequency profiler. It has 4 beams at 3 MHz and 1 vertical beam at 1 MHz to measure depth. The velocity profiling range is between 0.3 and 5 meters when using bottom track. Both of these profilers use River Surveyor Live on a PC. The River Surveyor comes with manufacturer-supplied options for wireless communications, for GPS, and also for tethered boats. The River Surveyor ADCPs do not require the user to manually configure the ADCP for river conditions. The River Surveyor ADCPs automatically change frequency, ping type, and/or water mode and cell size dynamically as the ADCP moves across the river. The River Surveyor continuously tracks the water velocity and depth. Based on these values, it selects the optimum processing configuration. The River Surveyor, using Smart Pulse HD mode, runs multiple ping types from multiple frequencies at the same time. The River Surveyor may use a total of 8 to 10 different ping types, but 3 to 5 simultaneous ping types are typical. The parallel processing capabilities allows the system to collect new acoustic pings while at the same time analyzing data from the last set of pings. This continuous evaluation of data allows the system to modify the operation on a second-by-second basis to ensure it always uses the best ping types for the conditions at the moment. Lastly, a separate ping from the vertical beam is used to measure depth. For the M9, up to 3 frequencies are used: 3 MHz, 1 MHz, and 0.5 MHz. Both depth and velocity determine the frequency and ping type used. 3 MHz pulse coherent is used if the depths are less than 1.5 meters and the velocity at that 1.5 meter depth is less than 0.4 meters per second. The velocity threshold increases with shallower depths. A 1 MHz pulse coherent mode is used if the depths are less than 5 meters and the velocity at the 5 meter depth is less than 0.4 meters per second. Again, the velocity threshold increases with shallower depths. A 3 MHz incoherent mode is used for velocities exceeding the 0.4 meters per second at 5 meter depth, with cell sizes increasing with the depth range. For the S5, both depth and velocity determines the ping type used. The 3 MHz pulse coherent mode is used if the depths are less than 1.5 meters and the velocity at that 1.5 meter depth is less than 0.4 meters per second. Like the M9, that velocity threshold increases with shallower depths. The 3 MHz incoherent mode is used if the velocity is greater than 0.4 meters per second at the depth of 1.5 meters. The depth cell sizes increase with depth range. The River Surveyor RS5 is the newest ADCP in the River Surveyor line. The RS5 is self-contained, having the battery and wireless communications built into the ADCP. SonTek offers 2 GPS options. The RS5 is a broadband ADCP. To avoid loss of data due to communication glitches, data buffering is built in to span data losses up to 5 minutes. The RS5 is small, but still contains a vertical beam. All beams are 3 MHz, and the slant beams are at a 25-degree angle. The RS5 will bottom track to about 5 meters and measure depths up to 6 meters. The minimum cell size is 2.5 centimeters. The RS5 has both auto-adaptive and manual configuration options. Details on the manual configuration options are provided in the RS5 user manual. However, I do not have a description of the characteristics of the auto-adaptive mode. The ADCPs we have just discussed are similar in how they profile the water column. Doppler measurements are inherently noisy. They have a lot of random error. Long lags are more accurate, but limit the maximum velocity and depth that can be measured. Averaging noisy or random data lead to more accurate measurements. The way to compensate for this noise or randomness is to either ping faster, use the broadband approach, and/or use bigger bends. Small bends are noisier than larger bends because larger bends allow more data to be collected within the bend. We often think of the profile collected by an ADCP to be similar to a profile that could be created by having a whole string of velocity meters deployed vertically, with each meter measuring the velocity in a discrete layer. However, the ADCP bends are not independent of each other. This diagram shows 2 important points. The lag moves the top of the first cell further from the water surface and the last cell further from the stream bed. The velocity reported at the center of the depth cell is center weighted, and the data from an area extending nearly 1 cell above and 1 cell below the center line are included in the velocity reported at the center of the depth cell. For pulse coherent modes, there is not the need to weight a lag, as the pings in the pulse pair are independent. Thus, pulse coherent modes can measure closer to the water surface and closer to the stream bed. Gartner and Ganju published a paper in 2002 that identified a potential problem with ADCP measurements. They made measurements from a bridge using an ADCP and also a point velocity ADV. When they compared the data, they observed that the velocities measured by the ADCP near the ADCP appeared to be biased low when compared to the ADV measurements. After investigating several potential sources of error, the conclusion was that it must be due to disturbance of the flow by the ADCP and not from any signal processing issue in the ADCP. I used a commercial three-dimensional computational fluid dynamics model, Flow3D, to model the flow around an ADCP. I then projected the beams through the computational grid and computed what the ADCP would measure given that flow condition. Thus, the ADCP signal processing was not involved. I only used the transformation of the beam velocities obtained from the CFD model and transformed them into horizontal and vertical velocities that the ADCP would have measured in those conditions. The model data is shown in red, and the average field data obtained by Gartner and Ganju is shown in blue, with the individual profiles measured by Gartner and Ganju shown in the light black lines. Thus, the model closely replicated the field results and validated that the bias was due to flow disturbance rather than anything in the acoustic processing algorithms. The reason for the bias is due to the assumption of flow homogeneity. The graphs on the left show the downstream velocity contours, and the graphs on the right show the vertical velocity contours. The plots on the top are for an isolated ADCP, and the plots on the bottom are for an ADCP deployed in a tethered boat. What we can see is that the velocity as it approaches the ADCP dives to get under and around the ADCP and then recovers as it passes past the ADCP. Thus, any of the beams pointing forward see a downward velocity, and the beams in the rear pointing rearward see an upward velocity. This combination violates our homogeneity assumption made for the equations to transform beam velocities into horizontal components and leads to a low bias in the measured velocities within the disturbed region. To further test this finding, data were collected in cooperation with the Lower Colorado River Authority with a SonTek M9 and a TRDI StreamPro. The StreamPro had been modeled and showed little to no effect of flow disturbance due to its small size. The bias in the M9 data and lack of bias in the StreamPro is clearly shown here in these graphs. The M9 in each of these graphs is using a different deployment, but they all show this tendency towards a negative bias near the transducer that is not evident in the StreamPro data. Modeling this data shows a very close correlation between the model results and data measured in the field. Based on that investigation, the default blanking distance is adequate to avoid the bias for RiverRay, RiverPro, StreamPro, S5, and the M9 when using 1 MHz beams. However, it is recommended that the measured data not be used within 16 centimeters of the transducer for the M9 and within 25 centimeters of the transducer for the Rio Pro. The ADCP cannot measure the entire water column. At the top, the ADCP must be deployed in the water and submerged, so we have the ADCP draft, or depth below the water surface. We also have the blanking distance, the distance that sound travels while the transducer stops vibrating from the transmission and becomes quiet enough to accurately record the reflected acoustic signal. The ADCP also cannot profile to the bottom due to interference by the side lobes. When sound is transmitted, most of the acoustic energy is contained in the main beam. However, there are also side lobes. These side lobes contain less energy. The reflection of the main beam from the scatterers returns only a small amount of the initial energy from the transducers. Although a side lobe has a small amount of energy, it can take a more direct path to the stream bed, and it reflects substantially more of the initial energy when it is reflecting from the stream bed. The result is, at the transducer, the amount of energy in the main beam is nearly equal to the energy from the side lobe for the region near the stream bed. Assuming the side lobe takes a vertical path to the stream bed, the side lobe cutoff threshold can be determined as the cosine of the slant beam angle times the water depth. For a 20-degree system, that is 94% of the range from the ADCP to the stream bed. The lower 6% cannot be measured. For a 30-degree river ray, the lower 14% cannot be measured. And for a 25-degree SonTek ADCP, the lower 10% cannot be measured. To avoid any interference from the side lobe, profiling must be terminated a lag before the side lobe cutoff. TRDI uses the shallowest beam to determine the side lobe cutoff. SonTek typically uses the average beam depth. Part 3 of this session, we will look at bottom tracking. The water velocity measured by an ADCP deployed on a moving boat is the velocity of the water passing by the ADCP, which is referred to as the relative water velocity. It is relative to the instrument. This relative water velocity includes the velocity of both the boat and the water. Therefore, as the boat moves faster, the relative water velocity measured by the ADCP increases. Since we are interested in the actual water velocity referenced to a fixed location, the velocity of the boat must be measured and removed from the relative water velocity measured by the ADCP. In addition to measuring the water speed using the Doppler shift, the ADCP can also measure the speed of the instrument or boat by measuring the Doppler shift of a pulse off the river bottom. This is called bottom tracking and assumes the stream bed is stationary. Bottom track acoustic pulses are separated from water track pulses. Bottom track pulses can be long, up to 20% of the depth. Because of this, sediment transported on the stream bed or near the stream bed can be within the long pulse and can affect the Doppler shift of the bottom track pulse, which can result in the measured boat velocity being biased in the opposite direction of sediment transport. This bias in the boat velocity, which results in a water velocity bias, is referred to as a moving bed condition. A moving bed condition will cause an apparent increase in the upstream boat velocity. Given this increase in boat velocity, the relative water velocities will be corrected with a boat velocity that is too high. The result is the measured water velocities will be biased low, resulting in a discharge that is biased low. The discharge bias due to a moving bed is always low. Collecting additional data will not help. It is a bias error, not a random error. This is a screen capture of a stationary moving bed test collected with a TRDI ADCP using differential GPS. The GPS data are shown in blue and the bottom track data are shown in red. As can be clearly seen, the boat moves slightly, but the bottom track shows a steady increase movement in the upstream direction. This is a screen capture of a transect collected with a SonTek river surveyor using differential GPS. The stick ship track plot illustrates the measured movement of the boat referenced to bottom tracking, the blue line, and the GPS, the orange line. Notice in the illustration that the bottom tracking boat path is shifted in the upstream direction relative to the GPS ship track. This is a result of a moving bed at the site. However, when analyzing these types of plots, it is critical that the compass was properly calibrated, that the magnetic variation is properly set, and that there are no sources of compass error that may change as the boat moves through the section, or the difference between the bottom track and the GPS could be compass related and not due to a moving bed. In addition to measuring water and boat velocity, the ADCPs also measure depth. All of the ADCPs determine the depth from the bottom tracking ping. It is possible that the ADCPs measure a valid depth without measuring a valid boat velocity. It is also possible that one or more of the beams may be invalid or have a multiple reflection. The depth of the ensemble is often taken as the average of 4 beams. The M9, RS5, River Pro, and most river rays also have a vertical beam that can be used for the depth of an ensemble. The RSSI is the reflected signal strength indicator or backscatter intensity. If you look at the intensity profile in Wind River and turn Mark Bad Below Bottom off, you may see a display that looks like this. The backscattered energy decreases with depth, but when it hits the stream bed, significantly more energy is reflected back, and we see a huge spike in the RSSI. These are the results of water pings, but the bottom ping would be similar. Note the second spike below the bottom. This is called a multiple and is caused by the acoustic signal reflecting from the stream bed, returning to the water surface, reflecting from the water surface, and reflecting again from the stream bed a second time. It is approximately twice as deep as the first peak. Sometimes in one or more beams, the multiple gets digitized as the depth rather than the actual depth. This is shown in this contour plot from Wind River 2. Processing software often have algorithms to filter out these false depths. When using the depths from the 4 slant beams, the average depth can be computed in 2 ways. First, the depth can be computed as a simple average. Using the diagram at the right and assuming the 4 beams are at 90 degrees from each other, the 4 beam depths would be 15.7, 10, 7.3, and 10. The simple average results in a depth of 10.75. The depth is biased deep when the 4 beams are measuring the depth of a slanted surface. The bias can be reduced by using an inverse depth-weighted average. The weight given to each beam is computed as 1 minus the ratio of the depth of the beam to the sum of all the beam depths. Using the inverse depth-weighted average yields a value of 10.46. Still not the actual depth of 10 below the ADCP, but less biased than the simple average. Using the vertical beam will provide a more accurate representation of the cross-section, particularly when there are sharp changes in the slope, such as in this trapezoidal section. So which should you use, a 4-beam average or the vertical beam? In my opinion, there is not a clear answer. While the vertical beam provides a better representation of the cross-section along the center line of the ADCP, the velocities are measured from the slant beams. Since the velocity is not measured directly below the ADCP, are the depths from the slant beams better correlated with the measured velocity for computing discharge? I don't know. Because the majority of the original comparison data to validate the use of ADCPs for measuring discharge were made before the vertical beam was available, and the fact that the slant beams are used for boat and water tracking, I personally tend to lean towards the 4-beam average. But I'm also not aware of any bias caused by using the vertical beam, except for the early River Ray firmware versions. So which should you use? The choice is really yours. Hopefully, from this lengthy discussion, you have a better understanding of how ADCPs work and the limitations of the ADCP.